Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to learn about subproblems and overlapping subproblems. When I first started learning about this topic years ago, I found it challenging because I would hear phrases like, if you find the overlapping subproblem, you can solve this using dynamic programming. Or, if you have subproblems, you can use divide and conquer and solve it recursively. But I've still found there aren't many great resources into breaking down what exactly a subproblem is in a simple and effective manner. So in this lesson, we're really going to start from the basics, make sure you understand them thoroughly, and really feel confident using them in your interviews. So we'll start by defining the term subproblem. What we mean by a subproblem is we take a function and call it multiple times, but with slightly different input values each time. So each time we modify the input value, we're solving a different subproblem, and then we can combine the results of all these different subproblems into our overall solution. So there's a bottom-up approach where we just start with the smallest value and build it up until we reach the solution that we want. Or we can go top-down where we recursively call functions and we have a smaller input value each time until we get to the base case. Then, we combine the result of all the function calls to get our overall solution. So a very simple example of this is the factorial function. We know the factorial of n is n times the factorial of n minus 1. And this is where we see subproblems. We can't find the factorial of a number until we find the factorial of the number before it. So we have to continually solve this factorial function to calculate the factorial of the nth item, and those are subproblems, calculating the factorial with different input values. So if we have 4 factorial, this is just 4 times 3 factorial. Then 3 factorial is 3 times 2 factorial, and so on. So we keep solving this factorial function with different values. So let's walk through exactly how that builds up. We start with factorial 4. Factorial 4 is just 4 times the factorial of 3. So now we're solving this subproblem with a different input value. Then, to solve the factorial of 3, we do 3 times the factorial, and we change the input value again to 2. So now we're solving these subproblems to find the factorial of 4. Then, to find the factorial of 2, we do 2 times the factorial of 1, so change the input again, so a new subproblem. And now we hit the base case. The base case always returns a constant value, so using this, we are able to start calculating the answers to our individual subproblems, and then building those up and combining them to get our overall solution where we want to find the factorial of 4. Or, we could continue to combine them and calculate the factorial of any number by continuing to solve these subproblems. So the base case returns 1, then we do 2 times 1 is 2, then we can return this up to chain. We do 3 times 2 is 6, then we return this up again, so now we solve the subproblem 3 times, and then finally we get back to our original call, we do 4 times 6, and we calculate the factorial to be 24. So we can calculate the factorial of any number that we want by first just calculating the factorial of all the numbers before it and treating each of those as their own individual subproblems that take different input values. So each of these boxes represents a subproblem. We're using the exact same code in each one, but we're just changing the input value. For the first subproblem, we just call factorial of 4, or use 4 as the input to this subproblem, and then we do 4 times the factorial of 3. So all we're doing is changing the input value, but then we call this function again. Factorial of 3 is just 3 times the factorial of 2. So this is another subproblem that we need to solve, which is the factorial function with the value of 2. Then this subproblem, factorial of 2, is just 2 times the factorial of 1. So now we need to solve the subproblem again, factorial of 1, which then this hits our base case. So this subproblem is solved, so then we use its value and use it in the subproblem that called it. So 2 times 1 is 2. So then we return this value to the subproblem that called it, which is the factorial of 3 subproblem. And we do 3 times the value of 2, which is just 3 times 2 times 1, which is exactly the factorial of 3, which gives us 6. Then now that we've solved the factorial of 3 subproblem, we can use its value in the factorial of 4 subproblem, which is 4 times 6, which is equivalent to 4 times 3 times 2 times 1, or the results of our previous subproblems. And this is how we combine subproblems. We solve this function or use the same code with different input values, then we get its result, and then use the smaller values result in the subproblem that called it until we build up the solution and reach the original function call that started these recursive calls to solve all these subproblems. And then once we solve this subproblem, it also gives us the overall solution. So solving the factorial is a subproblem, but it's not overlapping. So now we're going to talk about overlapping subproblems. An overlapping subproblem means you're solving the same subproblem multiple times, or calling it with the same input multiple times. So maybe the easiest to understand is Fibonacci. To calculate the nth Fibonacci number, we can see it's a subproblem because we're calculating the Fibonacci number with different values. So Fibonacci of the n is the Fibonacci of the n minus 1 plus the n minus 2. So if we want to calculate the 10th Fibonacci number, that's Fibonacci of the 9 plus Fibonacci of the 8. So 2 different subproblems that we're solving. But then to calculate Fibonacci of the 9, we also need Fibonacci of the 8, and then we do plus Fibonacci of the 7. To calculate Fibonacci of the 8th number, we again need Fibonacci of the 7 plus Fibonacci of the 6. So not only is this a subproblem because we're calculating the Fibonacci number for different values, it's overlapping because we have to calculate the Fibonacci number for the same value multiple times. For example, we're calculating Fibonacci of the 8 for Fibonacci of the 10 and Fibonacci of the 9. We calculate the 7th Fibonacci number for both Fib 9 and Fib 8. So this repetition is where the overlapping comes into play. So we can use a tree data structure to visualize recursion. Here we're calculating the 7th Fibonacci number, and we do so by calculating the 6th Fibonacci number and the 5th Fibonacci number. And by using this tree, we can see all this branching creates more and more recursive calls. So even though we only want to calculate the 7th number in the sequence, it creates so many extra calls. That's because the overlapping subproblems. We call the Fibonacci function with the same input many, many times. The numbers that have no background are the first time that that number is called as the input to the Fibonacci function. But then these blue numbers indicate that you're calling the function with the same value again. So we can see that we calculate the second Fibonacci number 1, 2, 3, 4, 5, 6, 7 times. And that's why it's overlapping. It's just calculating the same thing over and over and over. So when you see this tree structure, when you see all this branching, it can be a very good indication that you do have overlapping subproblems. So now, let's compare this Fibonacci recursive representation to a factorial recursive representation. We know both factorial and Fibonacci have subproblems, but only Fibonacci has the overlapping subproblems. So that's where all the branching comes from, but the factorial has no branching. So instead of a tree, it's really more of a linked list, where it's a straight line from the beginning to end, or from the top number to the base case, and then the base case back to the top number. So the factorial function is only called with each input at most once. And this is in contrast to something like a Fibonacci recursive representation, where each function call spawns 2 additional function calls, because any given Fibonacci number needs the 2 Fibonacci numbers before it. So with Fibonacci, we create this recursive tree. And a recursive tree can be an indication that you have overlapping subproblems, but it's not always guaranteed. You know you have overlapping subproblems when you call the function with the same value multiple times. And when we have these same values called multiple times, we're doing repeated work. And we're going to see that we can use a concept called memoization to remove this repeated work and reduce our time complexity. So now I hope you have a better understanding of what subproblems are and what it means for a subproblem to be overlapping. A subproblem means that we solve the same function with different input values each time, getting smaller and smaller until we reach the base case. An overlapping subproblem means we're going to call the subproblem function with the same input value multiple times. So when we were solving the factorial subproblems, each input value only appeared once, and then we were able to calculate the overall solution. But with Fibonacci, we use the same value multiple times to calculate the solution. Thanks everyone, and I'll see you in the next lesson.